Hello, this will be a video covering the Unit 2 review. So for this first section here, I'm just going to sort of let you read through my answers, and if you have any questions about them specifically, you can come in and ask me, but I'll try and explain some of the more confusing bits, and other than that, it's kind of just a for your information sort of thing. So talking here about solid, liquid, and gas, you should know about their shape and volume. Solids, definite shape, definite volume. Liquids, variable shape, definite volume. Gas is variable for both. In terms of the way that they're organized, solids are really nicely organized. You can see here in this very close packed structure. Liquids are more disorganized and they fill the bottom of the container that they're in, and gases are sort of bouncing all around the container, and they're going to expand to fill whatever container they're in. All right, and so that's why they have the variable shape and the variable volume. Moving down here to question number 2, I think that this is a pretty good flow chart. So you're looking at all matter and you're trying to classify it. The first question you should ask yourself is, does it have a formula? If it does have a formula, then we're looking at a pure substance, which could be either an element or a compound. If it does not have a formula, then it's a mixture. In terms of the formula, then, you're looking at it, if it has just one capital letter in the formula, that means it's an element. If it has multiple capital letters in the formula, it's a compound, okay, because that means it has multiple elements in it that are chemically bound to one another. Elements are on the periodic table, compounds are not on the periodic table, so that's another way that you can kind of double check yourself on that. On the mixture side of things, you ask yourself, is this the same throughout? If it's the same throughout, then that means it's homogeneous. If it's not the same throughout, it's heterogeneous. As one thing here that you have to remember, homogeneous includes all alloys, and heterogeneous includes all colloids. All right, so you need to know that all alloys are homogeneous and all colloids are heterogeneous. So going on, classifying these things here, baking soda, we have a formula there, so it's a pure substance. It has multiple capital letters, so that makes it a compound. All right, different things chemically bonded together, sodium, hydrogen, carbon, and oxygen all in there. Graphite, I told you, is just carbon. Carbon is one element. It's on the periodic table, so graphite is a form of carbon, which is an element. Opal here, I tell you, is a colloid, so that makes it a heterogeneous mixture because all colloids are heterogeneous mixtures. Soda pop, it's a mixture. Hopefully it's homogeneous. Most of the time with beverages, assuming that it's going to be like the same, the first sip that you take and the last sip that you take is going to be the same. You would say it should be the same throughout. Soda gets a little weird because it's carbonated, but I'm still going to call it a homogeneous mixture. Rose gold is an alloy. All alloys are homogeneous mixtures. You should just memorize that again. Silver, it says Ag. That's got a formula. It's also on the periodic table, so that makes it an element. The formula only has one capital letter, so that confirms it's an element. Going on here to page number 2, different methods of separation. So I'm going to talk about each one here pretty quickly. Filtration, what's happening with that is you'll have a solid and a liquid mixed together. The solid doesn't dissolve, and so you can see it just sort of floating there in the liquid. You dump it through a filter. The non-dissolved solid gets caught in the filter, the liquid passes through, and you separate them that way. So this would be using a heterogeneous mixture where a solid was mixed in a liquid and not dissolved. For evaporation, what we have here usually, what we're trying to separate is a homogeneous mixture where a solid is dissolved in a liquid. All right, so like salt water where the solid gets dissolved into the liquid. That would not come out in a filter, but what you can do is you can use an evaporating dish and boil the liquid away and collect the solid. All right, you would only use this if you want to collect the solid. This isn't good for collecting the liquid because the liquid sort of floats off into the atmosphere and you can't recollect it again. So this is a method of separation if you want to collect the dissolved solid. It doesn't work if you want to collect the liquid. Distillation separates based on boiling point. There are a couple places we use this. One of them is if you have two liquids that are mixed together that have different boiling points. And then so you heat them up. The one that heats up the one that boils at a lower temperature would boil up into a tube. It gets cooled down in the tube and recondensed into another container. The other way that you can use this is if you have that situation like we talked about in evaporation where you have a solid that's in a liquid, but this time you're interested in purifying the liquid, you'll use distillation. So what you do is you'd have a flask where a solid was dissolved in the liquid. You'd boil it. The liquid would boil away. The solid stays in the original flask. The gas that is boiled away again, runs through that tube where it's cooled and it's recondensed into another container. All right, and so that can separate a solid and a liquid where the solid is dissolved in the liquid as well. Chromatography is best used when you have two solids inside of a liquid and you want to separate them. So this is the one where it separates based on how fast two substances move through what we call a medium. I used an example of what's called chromatography paper, which is sort of like a paper towel. Large things move slower than small things. So if you had something like sugar, which is a relatively large molecule, compared to sodium chloride, which is relatively small, the sugar would move slowly through the chromatography paper. The sodium chloride would move quickly. And so you get differing speeds through that, and you can separate them that way. All right, on to this section C, talking about chemical and physical properties, chemical and physical changes. It says, what's one way to distinguish between physical and chemical properties? Well, again, you can kind of just read through this, but physical properties you measure without changing the substance, or you don't have to chemically interact with the substance to measure a physical property. So examples I give below are length, mass, volume, temperature, density, boiling point, melting point, color, state of matter, etc. So these are all things, physical properties are all things that we can measure without actually modifying the substance or chemically interacting with the substance. A chemical property, you have to have like a little chemical reaction to test the chemical property. So taste and smell, acidity or pH, toxicity, reactivity, flammability, corrosiveness. These are all things where you'd have to do a little chemical test to see what they were, and so those are what we call chemical properties. And so the main difference is, does a chemical reaction have to happen to test the property, or is the material sort of modified through the course of a test for a property, in which case it's chemical. Otherwise, if you can just measure it without altering the substance or interacting with the substance at all, it's a physical property. Number 3, it says, what's the difference between chemical and physical changes? And so in this one, we're talking about changes now. And so this would be things like tearing something, light it on fire, boil it, et cetera, et cetera, et cetera. So in this case, a physical change means that you're doing something to it but not changing what it's made of. You're not changing its chemical composition. In a chemical change, we are going to change the chemical composition of what's involved. And so what you'll have here is a chemical reaction occur where some chemicals are used up, other ones are produced. All right, and that would be considered a chemical change. And so things like tearing something in half, mixing two things together that don't chemically react, painting over something, you're just covering a material in another material, moving something, those are all physical changes. Things like burning something or breaking, or mixing two chemicals and having them react or something like that, those are all chemical changes because new chemicals get formed. And then there are some signs here in number 4 that a chemical reaction or a chemical change has occurred. So if you see these things, it's evidence that you've got a chemical change on your hands. So light, heat, or sound is produced. A precipitate is formed. A precipitate is when you mix two liquids and a solid, like a cloudy solid forms inside the two liquids. And so for a precipitate, you could mix two things that look just like water, but when you mix them, they end up making this new cloudy substance, and that shows that a chemical change has probably occurred. You can see some bubbling or fizzing that's occurred that wasn't there originally. If there's a color change, that indicates that a chemical reaction has probably happened, or if an odor is released. Something that is not a chemical change, boiling or melting, those are physical changes, so be careful about that. Boiling, if you boil water, for instance, it's going from liquid water to gaseous water, but it's still water, so we're talking physical change here. Or melting something, if you have an ice cube and you melt it into a liquid water, again, you're melting it, but it's still staying water the whole time. So boiling and melting, or freezing and condensing, those are physical changes, not chemical changes. All right, so for these density problems, we're going to be using the algebra circle over there on the right. The other way, it says it wants you to write them in words as well. So the density equation in words is just density equals mass over volume. All right, or again, you can use the density circle. You have to have this memorized for the test. Just to remind you about how it works, you cover up what you're solving for. So if you want to solve for density, you cover up the D and you get mass over volume. If you want to solve for mass, you cover up the M. That would be density times volume because they're in the same row as each other. If you want to solve for volume, you cover up that we get mass over density. So that's how that works. Number 2 says, how does the density of a gold coin compare to the density of a gold bar? Well, if they're the same substance, density is a physical property of a substance, but it's also what we call an intrinsic property, meaning that it doesn't matter how much of the substance you have. And so whether we're talking about a small gold coin or a large bar of gold, it's still gold, all right? And so gold has a density of 19.3 grams per milliliter, and so they're the same, all right? What's different about these two objects is that the large bar of gold has more mass than the small gold coin, all right, but the densities of the two would be the same. Number 3, it says an object has a density of 4.5 grams per milliliter and a mass of 18 grams. What is the volume of the object in centimeter cubed? All right, so for this one, it's asking for volume. So if you cover up the V, again, you get mass over density. So volume equals mass over density, which is going to equal 18 divided by 4.5. All right, if you figure that out, you get 4. And then we're looking for volume. So in this case, it's grams per milliliter, so you get 4 milliliters. But if you realize that a centimeter cubed is the same thing as a milliliter, that was one of the big ideas from the density sheet. It's the same thing, so 4 centimeters cubed. All right, so those are the same thing. Okay, an object has a mass of 3,500 and a volume of 700. What is its density? So on this one, we're finding density, so you cover up the D. Density is mass over volume. So density equals mass over volume, which equals, in this case, 3,500 grams divided by 700 centimeters cubed. All right, 3,500 divided by 700, you should get 5 grams per centimeter cubed. So number 5 says, how do you determine whether or not an object will float? The way that you do this is if the density of an object is less than that of the liquid it's submerged in, Okay, so here's what you do. You look at the density of an object and you look at the density of the liquid you're trying to put it into. And again, if the object is more dense than the liquid, it sinks. If the object is less dense than the liquid, it floats. If they have equal density, it's called neutrally buoyant, which means it really doesn't sink or float. It just kind of stays where it is there. So that's that concept there. Section E here, we're talking about alchemy. So the first one's about proto-science versus modern science. You can kind of just read through that there, but proto-science has a lot of like magic and mythology and things like that in it, whereas modern sciences are based on like rational thinking and experimentation and empiricism, which is like using evidence to support arguments and things like that. So that's how those are different. Number 2, the main goals of alchemy, there are 3 of them. One of them is the Philosopher's Stone, which is the stone that turns base metals into gold, and it also gives you everlasting life and things like that. Also, transmutation was a goal, where they were taking one element and turning it into another element. And also, the last one there's this thing called the elixir of life, which if you drank it, it would like revitalize you, make you young again, things like that. So similar sort of to what the Philosopher's Stone does, but it's called the elixir of life. Number 3, geographically speaking, where did alchemy get its start and where was it developed after that? So first it started in this city of Alexandria. I mentioned this was in Egypt, but it was part of like empires that were built by the expansion of the Greek and Roman empires. And so like what happened here is you had some different sorts of people all mixed together. It was in Egypt. Alexandria is in Egypt, but it had like sort of Greek and Roman type thought happening in it. The city of Alexandria was where a bunch of scholars went. And so in that time period, because we couldn't communicate as easily, a lot of times scholars would all settle in one place. And the city of Alexandria, which I mentioned, had a really big, famous library there, was where a lot of scholars went to where they went to like communicate with each other and develop their ideas. And so Alexandria was where it really got its start. It was this sort of hive of intellectual activity. After that, Europe entered the Dark Ages, and the development of alchemy really went on in the Middle East during the Golden Age of Islam. There's this guy that I'll talk about here in number 4. I stink at pronouncing his name, but it's something like Jabir ibn Hayyan, who is an Arabic scholar, and he worked with ideas in alchemy, but more than that, what he did was he wanted people to go to a more systematic or experimental approach. And so you can see here that he's kind of working towards something that looks a lot more like chemistry than it does alchemy. And so some people consider this person to be sort of like the father of modern chemistry, like the first guy who did chemistry kind of as it is today. And so he's kind of the reason why chemistry sort of developed, alchemy sort of died off. He was a big person in that development there. And then the last thing here, as we're getting later and later in time, alchemists are getting less and less respect. People are going through like the Age of Enlightenment, and they're starting to see that a lot of this mysticism and things like that isn't true. And also, like the Catholic Church has sort of scorned the alchemist and things like that. And so people tend to not respect the alchemists very much anymore, and they're kind of thought of as low people, tricksters and thieves, and things like that. All right, I know that was pretty quick. If you have any questions over any of this stuff, please come in and ask. You can look over the practice exam if you want to get some extra practice with the stuff, or come in and talk with me and we can give you some extra problems or something along those lines.